Imagine walking into a facility so massive it has its own zip code. Across millions of square feet, hundreds of automated robotic arms move with sub-millimeter precision, gliding beneath ceiling-high HEPA filtration systems that keep the air tens of thousands of times cleaner than an operating room. On paper, this is the promised land of modern capitalism. With global automakers pouring hundreds of billions of dollars into electrification, owning a lithium-ion gigafactory looks like owning a mint. You take raw chemical powder, run it through automated machinery, and sell high-margin battery packs to desperate car companies lined up at your door. Here is the problem. Behind that sleek, high-tech facade sits one of the most unforgiving, cash-incinerating business models ever engineered. It is a business where a single speck of dust can cost you $2 million before lunchtime, where energy bills rival the gross domestic product of small island nations, and where a microscopic error in a chemical coating can bankrupt you 3 years after the product leaves the loading dock. A battery gigafactory is not really a technology business. It is a high-speed chemical refinery disguised as an assembly line, where your entire profit margin depends on eliminating invisible microscopic mistakes. To understand why, we have to look at the staggering math required just to open the front door. Building a modern battery factory capable of producing around 20 to 30 gigawatt hours of cells per year, enough to supply roughly 300 to 400,000 electric vehicles, requires an upfront capital expenditure between $2 and $4 billion. Let that sink in. Before you produce a single commercial cell, you are already billions of dollars in debt. The building itself is only a fraction of that cost. Roughly 60 to 70% of that initial investment goes straight into highly specialized machinery. You need massive industrial slurry mixers that cost tens of millions, continuous roll coating and drying ovens that stretch the length of a football field, and ultra-high-precision calendaring machines that compress chemical sheets down to tolerances thinner than a human hair. Then comes the hidden infrastructure cost that catches almost every newcomer off guard. The dry room. Lithium-ion chemistry hates moisture. If raw cathode or anode materials touch humid ambient air, the lithium reacts with water vapor to create hydrofluoric acid, ruining the materials and creating toxic gas. To prevent this, massive sections of the factory must operate inside an industrial-grade dry room where the relative humidity is kept below 0.5%, with dew points pushing minus 40 degrees. Running the industrial dehumidifiers and climate control systems required to maintain that atmosphere across several 100,000 square feet is not just expensive, it eats up 15 to 25% of the entire facility's baseline electricity budget every single day. Which brings us to the raw materials. Unlike software or consumer electronics, where raw materials make up a modest slice of the cost structure, raw material inputs account for roughly 70 to 75% of the total cost to build a battery cell. You are purchasing thousands of metric tons of processed cathode active materials, nickel, manganese, cobalt, or lithium iron phosphate, alongside specialized battery-grade graphite for the anodes, ultra-pure copper foil, aluminum foil, and proprietary liquid electrolytes. Because raw material costs are largely fixed by global commodity markets, you cannot simply negotiate them away. If raw materials cost $75 per kilowatt hour, and the market price for finished battery packs is hovering around $115 to $125 per kilowatt hour, your gross theoretical spread is only $40 to $50. Out of that tiny $40 spread, you must pay your engineers, service your billions in equipment debt, run your energy-intensive dry rooms, pay for shipping, and somehow pull out a net profit. And this is where we uncover the hidden mechanic that actually dictates whether a battery factory survives or goes bust: the scrap yield curve. In standard automotive manufacturing, if a stamping machine presses a fender incorrectly, you melt the steel down or rework the part. The loss is minimal. In battery manufacturing, once you mix chemical slurry, coat it onto foil, dry it, slice it, wind it, weld the tabs, inject the liquid electrolyte, and seal the pouch or can, there is no simple undo button. A flawed cell cannot easily be recycled on the spot. It is scrap. When a brand new gigafactory comes online, it does not launch with 95% efficiency. During the first 12 to 24 months of calibration, a new line often operates with scrap rates between 30 and 50%. Think about what that means mathematically. Imagine two factory lines, Factory A and Factory B, each running $100 million worth of raw materials through their machines each month. Factory A is a mature, dialed-in facility running at a 92% yield rate. Out of $100 million in raw materials, they produce $92 million in sellable grade A battery cells, discarding $8 million in scrap. Factory B is a new facility struggling with calibration, running at a 70% yield rate. They feed in the exact same $100 million of raw materials, the exact same energy, and the exact same labor. But Factory B produces only $70 million of sellable product, while $30 million of pure chemical value is thrown into the waste bin. In this business, a 10% swing in yield rate is not the difference between high profit and low profit. A 10% swing in yield rate is the difference between an 8% net margin and burning through $500 million of emergency cash reserves in 6 months. Yield rate is the entire business. This brutal operational reality is why geographic location is not chosen for cheap real estate. It is chosen around power grids and logistics. Radius. A full-scale gigafactory consumes between 100 and 200 megawatts of continuous power. That is equivalent to powering roughly 150,000 American homes. If your local utility charges 9 cents per kilowatt hour instead of 5 cents, that 4-cent difference compounds into tens of millions of dollars in added operational expenses every single year. Furthermore, shipping finished lithium-ion battery packs over long distances is an economic and regulatory nightmare. Fully assembled battery packs weigh between 1,000 and 1,500 pounds each and are legally classified as Class 9 hazardous materials due to thermal runaway risks. You cannot simply load thousands of them onto cheap standard freight and ship them across the country. As a result, the overwhelming majority of battery gigafactories are built within a 3 to 4 hour trucking radius of the automotive assembly plants they supply. If you build outside that critical cluster, your freight and hazardous transit insurance costs will erase your margins before the trucks reach the interstate. Then there is the hidden psychological dynamic of the business-to-business relationship between battery makers and traditional automakers. Automakers are notoriously ruthless clients. For over a century, legacy car manufacturers have dictated terms to Tier 1 suppliers, squeezing them for annual 3% price reductions while demanding multi-year warranty indemnities. When an automaker signs an offtake agreement with a battery plant, they don't just buy cells, they lock in contractual performance specs down to the millivolt and milliampere hour. If a vehicle manufacturer experiences battery degradation or field fires 2 years down the road, their legal teams immediately look to the cell supplier for reimbursement. This creates a massive, looming balance sheet liability that almost no casual observer accounts for. Warranty reserves and quality escrow. To protect against catastrophic recalls, battery manufacturers are forced to set aside hundreds of millions of dollars in restricted warranty reserve funds. One bad production batch that escapes internal testing can trigger an automotive recall costing over $1 billion. We saw this exact dynamic play out in the real world with the high-profile failure of Britishvolt in the United Kingdom, alongside the staggering challenges faced by European battery manufacturer Northvolt. Britishvolt set out with grand ambitions to build a multi-billion-dollar gigafactory in northern England, promising to power the next generation of British electric vehicles. But they underestimated the sheer velocity of capital burn required during the pre-production and tooling phase. Without a fully commercialized chemistry, proven manufacturing yield data, or ironclad off-take contracts from major automakers willing to underwrite their equipment loans, the company burned through hundreds of millions in investor capital before laying a single production-grade electrode, ultimately collapsing into administration. Even established giants faced this structural wall. When General Motors had to recall over 140,000 Chevrolet Bolts due to manufacturing defects in cells supplied by LG Energy Solution, the total cost exceeded $2 billion. LG ultimately agreed to pay GM roughly $1.9 billion. To cover the recall, that single incident demonstrated the core lesson. The financial penalty for a microscopic manufacturing flaw does not match the price of the battery. It scales to the cost of the entire vehicle. So how do the economics work when you look at the actual profit and loss sheet? Let's run the numbers on a standardized 20 gigawatt-hour operational facility producing cells at a baseline cost of $85 per kilowatt-hour and selling them to an OEM partner at $105 per kilowatt-hour on paper at 20 gigawatt-hours of annual volume. Total annual revenue sits at $2.1 billion. Direct raw materials at 70% of cost eat up $1.19 billion. Direct factory labor, engineering staff, and continuous maintenance consume roughly $220 million. Facility electricity. Dry room climate control. And industrial gases consume another $150 million. Equipment depreciation, writing. Down that $3 billion of machinery over an 8 to 10 year life cycle takes $300 million off the top line. Insurance, hazardous freight, regulatory compliance, and warranty reserves take another $100 million. In scenario A, the fully optimized, blue sky operation, the factory achieves a world-class 92% scrap yield. Total production costs remain contained, warranty claims stay near baseline, and the facility generates roughly $140 million in net operating profit. That represents an operating margin of roughly 6.5 to 7%. It is a solid, steady return on an industrial asset, but far from tech sector windfall profits. Now look at scenario B, the standard operational friction scenario. In this scenario, global prices for battery-grade lithium or nickel spike slightly, but your multi-year fixed-price contract prevents you from passing the full cost to the automaker. Simultaneously, a calibration issue on the electrode coating line drops your annual scrap. Yield from 92% down to 84%. That 8%. Drop-in yield incinerates over $140 million worth of raw chemical materials directly into scrap. At the same time, your utility rates adjust upward by 1.5 cents per kilowatt hour, adding $20 million to your annual overhead, just like that, without losing a single customer, without suffering a catastrophic fire, and while operating at full nameplate capacity, your $140 million profit converts into an $80 million annual net loss. That is the stark reality of modern Gigafactory economics. The transition to electrification is creating the largest industrial retooling in modern history, but the companies building the physical foundations are walking in razor-thin financial wire. Success in this business isn't won in the boardroom with visionary slide decks or billion-dollar press releases. It is won on the factory floor, micron by micron, in the relentless war against scrap.